Welcome to the global community of learners on the unccelearn.org site. You are going to be doing 5 courses. 1. The introductory e-course on climate change. 2. Children and climate change. 3. Cities and climate change. 4. Human health and climate change. 5. The open online course on gender and environment. Introduction to climate change science. This section provides an introduction to basic concepts of climate change science such as weather, climate, the greenhouse effect, climate forcings, and natural climate fluctuations. It then discusses main causes and elements of anthropogenic, human-caused climate change, including observed and projected changes in the surface temperature. The section concludes with a short discussion of climate change science, its importance and historical development. What is climate? It is important to understand the difference between weather and climate. What is happening in the atmosphere at any given time is considered weather, including, for example, wind speed and direction, precipitation, barometric pressure, temperature, and relative humidity. Weather changes in the short term, for example, daily, weekly, monthly. Climate is average weather and occurs over long time frames, for example, 30 years. A common confusion between weather and climate arises when scientists are asked how they can predict climate 50 years from now when they cannot predict the weather a few weeks from now. The chaotic nature of weather makes it unpredictable beyond a few days. Projecting changes in climate, i.e. long-term average weather, due to changes in atmospheric composition or other factors is a very different and much more manageable issue. As an analogy, while it is impossible to predict the age at which any particular man will die, we can say with high confidence that the average age of death for men in industrialized countries is about 75. Further information. The IPCC defines climate as follows. Climate, in a narrow sense, is usually defined as the average weather, or more rigorously, as the statistical description in terms of the mean and variability of relevant quantities over a period of time ranging from months to thousands or millions of years. The classical period for averaging these variables is 30 years, as defined by the World Meteorological Organization. The relevant quantities are most often surface variables, such as temperature, precipitation, and wind. Climate, in a wider sense, is the state, including a statistical description of the climate system. Complexity of the global climate system. In a broader sense, climate is the status of the climate system, which comprises the atmosphere, the hydrosphere, the cryosphere, the surface lithosphere, and the biosphere. These elements all determine the state and dynamics of the Earth's climate. The graphic illustrates a number of both natural and human factors that have an influence on the climate. An important mechanism within the climate system is the greenhouse effect, which is explained in the following slide. Further information. The atmosphere is the envelope of gas surrounding the Earth. The hydrosphere is the part of the climate system containing liquid water at the Earth's surface and underground, for example, oceans, rivers, lakes. The cryosphere contains water in its frozen state, for example, glaciers, snow, ice. The surface lithosphere is the upper layer of solid earth on land, and oceans supporting volcanic activity which influence climate. The biosphere contains all living organisms and ecosystems over the land and in the oceans. What is the greenhouse effect? The temperature of the Earth results from a balance between energy coming into the Earth from the Sun, solar radiation, and the energy leaving the Earth into outer space. About half the solar radiation striking the Earth and its atmosphere is absorbed at the surface. The other half is absorbed by the atmosphere or reflected back into space by clouds, small particles in the atmosphere, snow, ice, and deserts at the Earth's surface. Part of the energy absorbed at the Earth's surface is radiated back or readmitted to the atmosphere and space in the form of heat or thermal energy. The temperature we feel is a measure of this heat energy. In the atmosphere, not all thermal radiation emitted by the Earth reaches outer space. Part of it is absorbed and reflected back to the Earth's surface by greenhouse gas, GHG molecules and clouds, the greenhouse effect, leading to a global average of around 14 degrees centigrade, well above the -19 degrees centigrade, which would be felt without the natural greenhouse effect. The concentrations of some GHGs, such as carbon dioxide, CO2, are significantly influenced by humans. Others, such as water vapor, are not. Further information. The two most abundant gases in the atmosphere, nitrogen, comprising 78% of the dry atmosphere, and oxygen, comprising 21%, exert almost no greenhouse effect. Instead, the greenhouse effect comes from molecules that are far more complex and much less common. Water vapor is the most important greenhouse gas, and carbon dioxide, CO2, is the second most important one. Methane, nitrous oxide, ozone, and several other gases present in the atmosphere in small amounts also contribute to the greenhouse effect. NASA video on the greenhouse effect. In the video, we understand how water vapor, carbon dioxide, and other gases cause the Earth's greenhouse effect. Do you know how the greenhouse effect maintains the surface temperature of the Earth? This NASA's Earth Observatory video explains it in a graphical way.
Earth's greenhouse effect greatly affects climate. See if you can describe how carbon dioxide and water vapor cause the Earth's greenhouse effect. Also, see if you can describe how the greenhouse effect maintains the surface temperature of Earth. Scientists have long known that the presence of an atmosphere keeps the surface of the planet warmer than it would be without an atmosphere. In fact, without an atmosphere, the surface of the Earth would be about 30 degrees Celsius cooler than it is now. In order to understand why, we need to consider the surface of the Earth and its atmosphere separately. Because there is a radiative equilibrium, we know that the planet emits enough long-wave radiation into space to equal the solar radiation absorbed by it. However, most of the long-wave radiation that is emitted by the planet into space is emitted by the atmosphere rather than the surface of the Earth beneath it. Although the surface of the Earth does emit long-wave radiation, only about 10% of this radiation passes through the atmosphere and escapes into space. The rest is absorbed by clouds and by greenhouse gases in the atmosphere. There are many greenhouse gases, but the most abundant greenhouse gases are water vapor and carbon dioxide. Short-wave radiation from the sun passes through greenhouse gases, but long-wave radiation is absorbed by them. greenhouse gases absorb long-wave radiation that is emitted by the surface of the Earth. Subsequently, they re-emit the energy as long-wave radiation in all directions. About half of the re-emitted long-wave radiation does escape into space and contributes to the planet's radiative equilibrium. About half of the long-wave radiation emitted by the gases is directed back toward the surface of the Earth. As a result, a continual exchange of long-wave radiation takes place between the surface of the Earth and the atmosphere above it. The long-wave radiation contained in this exchange causes the warming effect known as the greenhouse effect. This phenomena is known as the greenhouse effect because, like the glass in a greenhouse, the atmosphere traps some of the energy beneath it. The greenhouse effect produces a warmer climate on Earth than would be possible without an atmosphere. In summary, water vapor and carbon dioxide allow solar energy to penetrate Earth's atmosphere but prevent much of the long-wave radiation emitted by the surface of the Earth from escaping to space. This trapping of long-wave energy is called the greenhouse effect and enhances the surface temperature of the Earth.
Factors shaping the climate. Climate forcings. The natural greenhouse effect is part of a balanced system of energy transfer and transformation within the atmosphere, at the Earth's surface and in the oceans. The Earth's climate remains largely stable because the energy received is equal to that lost. The energy budget is therefore balanced. However, there are factors that have caused major changes in the climate system. Since these factors drive or force the system to change, they are called forcings. The change in energy fluxes caused by these drivers are quantified by radiative forcing, RF. Positive RF leads to surface warming. Negative RF leads to surface cooling. During the last millennium, changes in the output of energy from the sun, volcanic eruptions, and increased concentration of greenhouse gases in the atmosphere have meant the most important forcings. Total radiative forcing has been positive and has led to an uptake of energy by the climate system. The graphic shows that the increase in the atmospheric concentration of CO2 since 1750 has become the largest contributor to total radiative forcing. Natural climate fluctuations. Example of El Niño and La Niña changes in the climate system due to climate forcings are not to be confused with natural climate fluctuations. Indeed, even within a relatively stable period, the systems that make up and influence the global climate still naturally fluctuate. These fluctuations, or oscillations as they are often called, because they oscillate between two main states, can have a large effect on the climate, both locally and on a global scale. One example is El Niño, La Niña, and the El Niño Southern Oscillation, ENSO. ENSO is a climate pattern that occurs roughly every 5 years across the tropical Pacific Ocean. El Niño, Spanish for little boy, describes extensive warming of the ocean's surface across the eastern and central equatorial Pacific, lasting 3 or more seasons. See the red area near the equator on the left globe. When this oceanic region switches to below normal temperatures, it is called La Niña, Spanish for little girl. See the blue area near the equator on the right globe. Climate change and global warming. Since the beginning of the 20th century, scientists have been observing a change in the climate that cannot be attributed to any of the natural influences of the past only. This change in the climate, also known as global warming, has occurred faster than any other climate change recorded by humans. The main cause of global warming is the increased concentration of greenhouse gases in the atmosphere since the Industrial Revolution in the late 18th century. The increased amount of gases which absorb and re-emit thermal radiation has directly led to more heat being retained in the atmosphere and thus an increase in global average surface temperatures. The increase in temperature is also leading to other effects on the climate system. Together, these effects are known as anthropogenic, human-caused climate change. Further information. Adding more of a greenhouse gas, such as CO2, to the atmosphere intensifies the greenhouse effect, thus warming Earth's climate. The amount of warming depends on various feedback mechanisms. For example, as the atmosphere warms due to rising levels of greenhouse gases, its concentration of water vapor increases, further intensifying the greenhouse effect. This, in turn, causes more warming, which causes an additional increase in water vapor in a self-reinforcing cycle. This water vapor feedback may be strong enough to approximately double the increase in the greenhouse effect due to the added CO2 alone. Observed change in surface temperature, 1901 to 2012. This diagram gives an indication of the observed change in average surface temperature between 1901 and 2012. It shows that almost the entire globe has experienced surface warming. According to the IPCC, the average global surface temperature has increased by 0.85 degrees centigrade over the period between 1880 to 2012. Tools to predict and project changes in the climate. Scientists have not only observed past changes in the climate, but also try to analyze possible future changes. For this purpose, they have developed a number of tools. Just as an architect might build a scale model of a building to understand and predict its behavior, so too climate scientists can build a computer-based model of the climate system to understand and predict its behavior. One of the inputs to a climate model are emission scenarios, which estimate future releases of greenhouse gases and aerosols to the atmosphere based on assumptions concerning, for example, future socio-economic and technological developments. The outputs of a climate model feed into a climate projection, i.e., a simulated response of the climate system to a certain emission scenario. This dependence on emission scenarios differentiates climate projections from climate predictions, which are based on conditions that are known at present, and assumptions about the physical processes that will determine future changes. Projected change in average surface temperature. This figure illustrates the projected, i.e., future change in average surface temperature for two different scenarios. The projections are for the end of the 21st century, 2081 to 2100, and are given relative to 1986 to 2005. The projection on the left is based on a scenario with relatively limited greenhouse gas emissions, RCP 2.6, while the projection on the right is based on a scenario with very high greenhouse gas emissions, RCP 8.5. RCP 2.6 projects an increase of 0.3 to 1.7 degrees centigrade in mean surface temperature compared to pre-industrial times, while RCP 8.5 projects an increase of 2.6 to 4.8 degrees centigrade by 2081 to 2100. Projections of changes in the climate system are based on a hierarchy of climate models that range from simple climate to intermediate complex models to comprehensive climate models as well as Earth system models. Based on a set of scenarios of anthropogenic forcings, the modules simulate changes. The Representative Concentration Pathways, RCPs, is a new set of scenarios that are used for the 5th assessment report of the Intergovernmental Panel on Climate Change, IPCC. Climate change has an impact. It has an impact on almost every aspect of our lives. Our ecosystems suffer biodiversity and habitat loss, and human systems like health will be negatively impacted. For example, the spread of disease vectors like mosquitoes. Climate change also challenges us to rethink our urban systems, including transport and buildings, and the way we do business, including green business opportunities. The impacts of climate change might also result in conflict or force people to migrate, for example, from low-lying coastal areas. Climate change science allows us to. Scientists worldwide are trying to better understand how the climate is changing, what changes we can expect in the future, and what role human activities play. While there is a debate about the likelihood of certain changes and their causes, broad scientific consensus exists that 1. Warming of the climate system is unequivocal, and 2. That human influence on the climate system is clear. Why is climate change science important? Climate change science provides important information for decision-making at various levels. For example, sound weather data and forecasts can help us determine when the best time would be to harvest our lands. It can also help us plan appropriately for emergency responses in case of climate-related hazards such as cyclones. Climate models help to forecast long-term climate scenarios and are important for proactive planning. History of climate change science. As far back as 1824, the French physicist Joseph Fourier is the first to describe the Earth's natural greenhouse effect. In 1861, the Irish physicist John Tyndall shows that CO2 and H2O can cause changes in the climate. In 1895, Swedish chemist Svante Arrhenius concludes that industrial age coal burning will enhance the natural greenhouse effect. In 1938, the British engineer Guy Calendar shows that temperatures had risen over the previous century due to increased CO2 concentrations. The Calendar effect is widely dismissed. In 1958, the geochemist Charles David Keeling was employed to continuously monitor CO2 levels in the atmosphere, with an increase in Antarctica visible after only 2 years. During the 1970s, other greenhouse gases, CH4, N2O, and CFCs were widely recognized as important anthropogenic greenhouse gases. And in 1979, the first World Climate Conference was held in Geneva, leading to the establishment of the World Climate Programme. In 1988, the Intergovernmental Panel on Climate Change, IPCC, was set up by the World Meteorological Organization, WMO, and the United Nations Environment Programme, UNEP. In 1990, the IPCC delivered its first assessment report on the state of climate change, predicting an increase of 0.3 degrees centigrade each decade in the 21st century. Section 2. Anthropogenic drivers of climate change. This section discusses the main driver of anthropogenic climate change. For example, the increased concentration of greenhouse gases in the atmosphere. The section starts with an overview of the most important greenhouse gases emitted by humans. It then discusses each gas in more detail, looking at 1. How significant the gas is in terms of global warming, and 2. How its concentration in the atmosphere has developed over time. The section concludes with a graph depicting the extent of the human influence on the climate system. This IPCC video on the human influence on the climate system. The Intergovernmental Panel on Climate Change, IPCC, has produced a video on the physical science basis of climate change. It looks at evidence of how the climate has changed in the past and present, what the causes of these changes are, and what possible future scenarios exist.
The scientific evidence is stronger than ever. Better and more observations. Improved understanding of the climate system response. Further development of climate models. All point in the same direction. Human influence on the climate system is clear.
IPCC 第5次评估报告第一工作组主要做的是气候变化的科学。它对这个过去6年以来气候系统各个科学的分支，所以呢，在气候系统的实际观测中证实气候系统正在变暖。
We have looked at all the evidences that tell us how the climate has changed in the past and presently, took that evidence to ask ourselves how we understand the climate system, what the causes of these changes are, and then take that knowledge and climate model simulation to ask ourselves what possible futures are there.
Many of these observed changes are unusual or unprecedented on timescales of decades to millennia. Ice cores contain an abundance of information about climate. Paleoclimate records show a close link between CO2 concentration and temperature. These trends are seen in current observations. Each of the last 3 decades has been warmer than all preceding decades since 1850, and the first decade of the 21st century has been the warmest.
Well, I think in AR5 we've done a much better job of expressing exactly how much different contributions, particular greenhouse gases, have contributed to global warming in the past and how they will contribute in the future. We're able to demonstrate that the CO2 concentration in the atmosphere has increased by 40% since pre-industrial times, mostly as a result of human activities, and that the levels of carbon dioxide in the atmosphere are higher than they've been for the last 800,000 years in Earth history.
The effects of global warming are most evident in some of the coldest places on the planet. Ice sheets and glaciers worldwide are losing mass, permafrost is thawing, and the snow and sea ice cover in the Arctic is decreasing.
We are getting a lot of signals from the cryosphere in terms of warming. The most visible signs of warming can be found in the Arctic.
Arctic sea ice extension has shown a downward trend since 1980. A downward trend is also observed at the Greenland ice sheet.
The amount of mass that's lost in Greenland is about 6 times as much as what was observed 10 years ago.
The observed changes in the cryosphere have serious implications. With less snow and ice, more of the sun's energy is absorbed by the ocean and land surface. This is one of the powerful climate change feedbacks that influences the whole climate system. Based on multiple lines of independent evidence, it's now virtually certain that the ocean is warming.
The warming of the ocean will continue even if we stop the atmospheric CO2 concentrations to increase, because the time scale of the ocean circulation, which connects the surface to the deep ocean, is very large in the sort of hundreds and thousands of years.
There are 4 major contributors to sea level rise: ocean heat uptake, melting of glaciers, reduction of ice sheets, and changes in water storage on land. Improved scientific understanding has made scientists able to make a consistent sea level rise budget.
Over the 20th century as a whole, the dominant contributions are ocean thermal expansion and the contribution from the loss of mass from glaciers. Sea level has risen by about 19 centimetres by 1900 to 2010, and it's continuing to rise. We will have to adapt to sea level rise.
Our understanding of the climate system relies on combining observations and studies from many different scientific disciplines. With the help of supercomputers, this knowledge can provide climate projections for the future.
Climate models play an absolutely crucial role in this assessment report. They are the only tools that allow us to say something quantitative about the future. Historically, climate prediction has started with predicting weather, the atmosphere, then we included the ocean, and now we're at the point where we include every component in the Earth system, including the carbon cycle and the chemistry. So that allows us to have a really comprehensive view of all the relevant processes for future climate change.
Climate change projections require information about future emissions or concentrations of greenhouse gases, aerosols, and other anthropogenic drivers. A new set of scenarios was used to project the cumulative CO2 emissions in the future.
Model simulations employing the RCP scenarios tell us we have a choice. We have a choice to live in a world in which climate change is limited to less than 2 degrees Celsius, or in a world that is warmer than 4 degrees Celsius.
Climate models employing the RCP scenarios provide policy-relevant information on a regional level. For the first time, Working Group 1 has developed an atlas of global and regional climate projections, which allows decision-makers to see how climate might change in their regions. This can facilitate more informed decisions on adaptation strategies.
We have 3 key messages. A warming in the climate system is unequivocal. That is based on the observations and the multiple lines of independent evidence. The second message is human influence on the climate system is clear. This is resulting from the combination of model simulations with the observed climate change. The third message is that continued greenhouse gas emissions cause further climate change and constitute a multi-century commitment in the future. Therefore, we conclude limiting climate change requires substantial and sustained reductions in greenhouse gas emissions.
Overview of greenhouse gases regulated under the Kyoto Protocol. Greenhouse gases, GHGs, are trace gases in the atmosphere that absorb and emit long-wave radiation. They naturally blanket the Earth and keep it at about 33 degrees centigrade warmer than it would be without these gases in the atmosphere. The table features the 7 most important greenhouse gases as regulated under the Kyoto Protocol. The 7 gases each have a different capacity to trap heat in the atmosphere, or a so-called global warming potential, GWP. They all belong to the group of long-lived greenhouse gases, LLGHGs, because they are chemically stable and persist in the atmosphere over time scales of a decade to centuries or longer, so that their emission has a long-term influence on climate. Some of the GHGs occur naturally, for example CO2, CH4 and N2O, but increases in their atmospheric concentrations over the last 250 years are due largely to human activities. Other greenhouse gases are entirely the result of human activities, for example HFCs, PFCs, SF6 and NF3. Further information. Kyoto Protocol. The Kyoto Protocol sets out legally binding targets for developed countries to limit or reduce their GHG emissions. It was adopted in 1997 and entered into force in 2005. Water vapor is the most important greenhouse gas, but since it is not produced by humans in any significant quantity, we have no control over its concentration in the atmosphere. It is therefore not regulated under the Kyoto Protocol. Global warming potential. Carbon dioxide is the baseline unit to which all other greenhouse gases are compared, and therefore has a GWP of exactly 1. A GWP is calculated over a specific time interval, commonly 20, 100 or 500 years, because some gases remain longer in the atmosphere than others. For example, the 100-year GWP of methane is 25, which means that if the same mass of methane and carbon dioxide were introduced into the atmosphere, that methane will trap 25 times more heat than the carbon dioxide over the next 100 years. Important greenhouse gases. Carbon dioxide, CO2. The most important anthropogenic GHG is carbon dioxide, CO2. It accounts for around 64% of total radiative forcing due to LLGHGs. Carbon dioxide does not have a specific lifetime because it is continuously cycled between the atmosphere, oceans and land biosphere, and its net removal from the atmosphere involves a range of processes with different timescales. CO2 is primarily emitted as a result of burning of fossil fuels, deforestation and forest degradation, and iron and steel production. Oceans and forests are the main sequesters of carbon, i.e. sinks that can absorb CO2 from the atmosphere. Carbon dioxide is the gas to which all other gases are compared when speaking of global warming potential. Emissions of other greenhouse gases can be converted into CO2 equivalent emissions. Further information. The contribution of each greenhouse gas to radiative forcing is determined by its global warming potential and the change in its concentration in the atmosphere over time. CO2 concentrations in the atmosphere and annual growth rates. CO2 levels in the atmosphere have been increasing steadily over the past 200 years. This is due to the increased use of fossil fuels, as well as an increase in deforestation, both of which release vast amounts of CO2 into the atmosphere. Today's concentration of CO2 is believed to be the highest it has been in the past 800,000 years. CO2 concentrations increased by about 100 ppm, parts per million, since the Industrial Revolution and exceeded the symbolic 400 ppm threshold at several atmosphere watch stations during 2012. Figure A shows the increase in CO2 concentrations between 1984 and 2012. Figure B shows the annual growth rate of CO2 concentrations during the same time period. Important greenhouse gases. Methane, CH4. The second most significant anthropogenic GHG is methane, CH4, which contributes to approximately 18% of total radiative forcing due to LLGHGs. Approximately 40% of methane is emitted into the atmosphere by natural sources, for example, wetlands and termites. About 60% comes from human activities, for example, cattle breeding, rice agriculture, fossil fuel exploitation, landfills, and biomass burning. Methane is mostly removed from the atmosphere by chemical reactions, persisting for about 12 years. Thus, although methane is an important greenhouse gas, its effect is relatively short-lived. CH4 concentration in the atmosphere and annual growth rates. This slide shows the atmospheric concentration of methane from 1984 to 2012 in Figure A, while Figure B shows the annually averaged growth rate. The concentration of CH4 has more than doubled since pre-industrial times, from approximately 700 parts per billion in 1750 to 1,819 parts per billion in 2012. Since 2007, atmospheric methane has been increasing again after a temporary period of leveling off. In focus, the carbon cycle. Carbon in its various forms, such as CO2 and CH4, is continually recycled on Earth and is never destroyed. The diagram illustrates the many ways in which carbon is released and stored in the environment. Carbon can be stored over relatively short periods in living organisms, for example plants and animals, or over thousands of years in the oceans. It can also be stored over millions of years in rocks or fossils. The diagram also shows how humans are affecting the carbon cycle. Before humans used fossil fuels for energy, the carbon cycle was relatively balanced, i.e., the total amount of carbon in the atmosphere stayed constant. By removing carbon from the long-term storage underground, oil, gas, etc., and putting it into the atmosphere, humans have tipped the balance of the carbon cycle, which in turn affects the global climate. Removing stored carbon through deforestation also further exacerbates this process. Important greenhouse gases. Nitrous oxide. Nitrous oxide is the third most significant GHG, contributing to about 6% of radiative forcing due to LLGHGs. The primary human sources of N20 are fertilizer production and use in agriculture and various industrial processes. It is estimated that N20 stays in the atmosphere for an estimated 114 years. Its impact on climate over a 100-year period is 298 times greater than equal emissions of carbon dioxide. It also plays an important role in the destruction of the stratospheric ozone layer, which protects us from harmful ultraviolet rays of the sun. N20 concentration in the atmosphere and annual growth rates. The concentration of N20 has been steadily increasing over the past 30 years. Its atmospheric concentration in 2012 was about 325.1 parts per billion, which is 20% more than the pre-industrial level, 270 parts per billion. Important greenhouse gases. Fluorinated gases. Fluorinated gases are a family of man-made gases used in a range of industrial applications. Sources include refrigerants, air conditioning, solvents, aluminium, and magnesium production. For example, many fluorinated gases have very high global warming potentials, GWPs, relative to other greenhouse gases. That means small atmospheric concentrations can have large effects on global temperatures. They can also have long atmospheric lifetimes, in some cases lasting thousands of years. Fluorinated gases are removed from the atmosphere only when they are destroyed by sunlight in the far upper atmosphere. In general, fluorinated gases are the most potent and longest lasting type of greenhouse gases emitted by human activities. There are three main categories of fluorinated gases: hydrofluorocarbons, HFCs, perfluorocarbons, PFCs, and sulfur hexafluoride, SF6. Further information. Hydrofluorocarbons, HFCs, are the most common group of F-gases. They are used in various sectors and applications, such as refrigerants in refrigeration, air conditioning and heat pump equipment, as blowing agents for foams, as solvents, and in fire extinguishers and aerosol sprays. Perfluorocarbons, PFCs, are typically used in the electronics sector, for example for plasma cleaning of silicon wafers, as well as in the cosmetic and pharmaceutical industry. In the past, PFCs were also used in fire extinguishers and can still be found in older fire protection systems. Sulfur hexafluoride, SF6, is used mainly as an insulating gas in high voltage switchgear and in the production of magnesium and aluminium. Greenhouse gases controlled by the Montreal Protocol. Some greenhouse gases are not included in the Kyoto Protocol because they are already regulated under the Montreal Protocol on substances that deplete the ozone layer, which entered into force in 1989. The Montreal Protocol includes, for example, chlorofluorocarbons, CFCs, which contribute about 12% to total radiative forcing by LLGHGs. CFCs can stay in the atmosphere for more than 1,000 years. CFCs have a global warming potential, GWP, that ranges between 4,750 and 14,400 over 100 years time spans. CFCs are used in the manufacture of aerosol sprays, blowing agents for foams, and packing materials, as solvents and as refrigerants. Concentrations of SF6 and halocarbons in the atmosphere. This slide shows the evolution of atmospheric concentrations of sulfur hexafluoride, SF6, the graph on the left, and numerous CFC and F gases, the graph on the right. Concentrations of CFCs, which are controlled by the Montreal Protocol, are in decline. However, hydrochlorofluorocarbons, HCFCs, and hydrofluorocarbons, HFCs, which are also potent greenhouse gases, are increasing at relatively rapid rates. Human influence on the climate system. This figure illustrates the important impact of human activities on the climate. It shows the contribution of different anthropogenic and natural factors to the observed temperature increase of about 0.6 degrees centigrade since 1951 on the black bar. The graph shows that GHGs such as carbon dioxide, methane, and nitrous oxide on the green bar are the main causes of the observed temperature change. The yellow bar depicts the influence of aerosols, tiny particles found in the atmosphere, which have a negative forcing effect, cooling on the climate. In fact, aerosols and their interaction with clouds have offset a substantial portion of positive radiative forcing by GHGs. Atmospheric aerosols are not to be confounded with aerosol sprays, which often contain GHGs and hence have a positive radiative forcing effect. Overall, human activity has led to positive radiative forcing, global warming, as indicated by the orange bar. Radiative forcing due to changes in energy output from the sun and volcanic eruptions only played a minor role in the reference period. Further information. Atmospheric aerosols are able to alter climate in two important ways. They scatter and absorb solar and infrared radiation. They may change the microphysical and chemical properties of clouds and possibly their lifetime and extent. The scattering of solar radiation acts to cool the planet, while absorption of solar radiation by aerosols warms the air directly inside of allowing sunlight to be absorbed by the surface of the Earth. The direct radiative forcing summed over all aerosol types is negative. Aerosols also cause a negative radiative forcing indirectly through the changes they cause in cloud properties. Section 3. Observed trends and impacts of climate change. This section describes some of the main observed changes in the climate since the Industrial Revolution. It looks at changes in surface temperature, precipitation levels, ocean warming and acidification, sea level rise, Arctic sea ice extent, as well as observed changes in physical and biological systems. The section concludes with a discussion of whether the recent increase in extreme weather events, such as cyclones and floods, can be attributed to anthropogenic climate change. Observed surface temperature anomaly, 1850 to 2012. This figure illustrates how the averaged land and ocean surface temperature has changed between 1850 and 2012. The annual temperature average has always varied, with cold and warm periods alternating. However, it is clear that each of the last 3 decades has been successfully warmer at the Earth's surface than any preceding decade since 1850. The temperature increase is widespread across the world, but there are important regional variations. Warming has been most marked in the northern polar regions. Observed change in annual precipitation over land observations show that changes are occurring in the amount, intensity, frequency, and type of precipitation. These aspects of precipitation generally exhibit large natural variability, and El Niño and other natural climate fluctuations have a substantial influence. Over the past century, however, pronounced long-term trends in precipitation amounts have been observed. Significantly wetter in Eastern, North and South America, Northern Europe and Northern and Central Asia, but drier in the Sahel, Southern Africa, the Mediterranean and Southern Asia. Moreover, widespread increases in heavy precipitation events have been observed, even in places where total amounts have decreased. The two maps show the observed precipitation change from 1901 to 2010 and 1951 to 2010. Observed ocean warming, 1950 to 2010. Ocean warming dominates the increase in energy stored in the climate system. Oceans account for more than 90% of the energy accumulated between 1971 and 2010. 60% of the net energy increase is stored in the upper ocean, 0 to 700 meters, and about 30% is stored in the ocean below, 700 meters. The ocean warming is largest near the surface, and the upper 75 meters warmed by 0.7 degrees centigrade per decade over the period 1971 to 2010. Observed ocean acidification. About 30% of anthropogenic CO2 emissions has been absorbed by the oceans. This leads to ocean acidification. The green curve in the figure shows the decreasing pH of ocean surface water since the late 1980s. According to the IPCC, the pH of ocean surface water has decreased by 0.1 since the beginning of the industrial era. Observed sea level rise, 1900 to 2010. The rate of sea level rise since the mid-19th century has been larger than the mean rate during the previous 2 millennia. Over the past century, global mean sea level rose by 0.19 meters. Glacier mass loss and ocean thermal expansion from warming together explain about 75% of the observed global mean sea level rise since the early 1970s. Observed decrease in Arctic sea ice extent 1900 to 2010. Over the last 2 decades, the Greenland and Antarctic ice sheets have been losing mass. Glaciers have continued to shrink almost worldwide, and Arctic sea ice has continued to decrease in extent. The graph illustrates the decrease in summer sea ice extent in the Arctic between 1900 and 2010. The spatial extent has decreased in every season since 1979. Observe changes in physical and biological systems. This slide shows a number of changes that have been observed in physical, blue, and biological, green systems between 1970 and 2004. Biological changes include, for example, species loss and ecosystem alterations. Physical changes include, for example, changes in snow cover, changes in glacier density, coverage, and runoff. The percentages associated with the observations indicate how many of the reported changes are due to a warming environment. In focus, is climate change to blame for extreme weather events? Whenever an episode of extreme weather, heat wave, flood, drought, etc. hits the headlines, many people tend to blame human-induced climate change. But what scientific evidence exists to explain individual extreme events, like a cyclone, with global warming? First of all, determining whether a specific single extreme event is due to a specific cause, such as increasing greenhouse gases, is difficult, if not impossible, for 2 reasons. 1. Extreme weather events are caused by a combination of factors. And 2. A wide range of extreme events is a normal occurrence even in an unchanging climate. At the same time, observations have shown a large increase in the number of strong hurricanes globally since 1970. Specifically, the number of strong hurricanes increased by about 75% since 1970. The IPCC points out that a trend towards longer storm duration and greater storm intensity is closely correlated with tropical sea surface temperature. This might be an indication of a causal link between global warming and hurricane destructiveness. However, the high variability in tropical storms and hurricanes over several decades and a lack of systematic high-quality observation before satellite observations make it difficult to detect long-term trends. Section 4. Projected trends and impacts of climate change. This section presents projected future trends and impacts of climate change on surface temperature, precipitation, ocean pH, sea level, and Arctic sea ice extent. The extent of these impacts depends on how anthropogenic emission levels will develop over the next decades. Therefore, the section presents impacts under a low emission scenario as well as under a high emission scenario. The section ends with a discussion of cumulative CO2 emissions and what different amounts of CO2 emissions would mean for the future climate. In focus, representative concentration pathways, RCPs. For the fifth assessment report of the IPCC, the scientific community has defined a set of 4 new scenarios, denoted representative concentration pathways, RCPs. These 4 RCPs include 1 mitigation scenario leading to a very low forcing level, RCP 2.6, 2 stabilization scenarios, RCP 4.5 and RCP 6, and 1 scenario with very high greenhouse gas emissions, RCP 8.5. The RCPs can thus represent a range of 21st century climate policies as compared with the no climate policy of the Special Report on Emissions Scenarios, SRES, used in the 3rd and the 4th assessment reports. Projected change in average surface temperature. Global surface temperature change for the end of the 21st century is likely to exceed 1.5 degrees centigrade relative to pre-industrial levels for all RCP scenarios, except RCP 2.6. It is likely to exceed 2 degrees centigrade for RCP 6 and RCP 8.5. Since the 3rd IPCC assessment report, confidence has increased that a 1.5 to 2.5 increase in global mean temperature above pre-industrial levels poses significant risks to many unique and threatened systems, including many biodiversity hotspots. Approximately 20 to 30% of species are at an increased risk of extinction if global average warming exceeds 1.5 to 2.5 degrees centigrade. Since the 3rd IPCC assessment report, confidence has increased that a 1.5 to 2.5 degrees centigrade increase in global mean temperature above pre-industrial levels poses significant risks to many unique and threatened systems, including many biodiversity hotspots. Approximately 20 to 30% of species are at an increased risk of extinction if global average warming exceeds 1.5 to 2.5 degrees centigrade. In terms of food security and human health, crop productivity for cereals in low latitudes would decrease, and the distribution of some disease vectors like mosquitoes transmitting malaria might change. Projected change in average precipitation. The IPCC projects that over the 21st century, the contrast in precipitation between wet and dry regions and between wet and dry seasons will increase. That means global warming increases risks of both drought and floods. Extreme precipitation events are particularly likely to become more intense and more frequent over most of the mid-latitude land masses and over wet tropical regions. The 2 maps illustrate projected changes in annual mean precipitation for the end of the 21st century under different scenarios. Under a low emission scenario, RCP 2.6 on the left map, changes in annual mean precipitation will not exceed 20% compared to 1986 to 2005 levels. However, under scenario RCP 8.5, the right map, significant changes in annual precipitation are to be expected. The high latitudes and the equatorial Pacific Ocean will experience an increase in annual mean precipitation, while in many mid-latitude and subtropical dry regions, mean precipitation will decrease. Further information. As climate changes, several direct influences alter precipitation amount, intensity, frequency, and type. Warming accelerates land surface drying and increases the potential incidence and severity of droughts, which has been observed in many places worldwide. However, a well-established physical law, the Clausius-Clapeyron relation, determines that the water-holding capacity of the atmosphere increases by about 7% for every 1 degree centigrade rise in temperature. Because precipitation comes mainly from weather systems that feed on the water vapor stored in the atmosphere, This has generally increased precipitation intensity and the risk of heavy rain and snow events. Temperature and precipitation projections for the 21st century video.
Who can tell what the future will be like? NASA scientists have combined data from several climate models used by the UN Intergovernmental Panel on Climate Change to show how patterns of temperature and precipitation could change through the end of the 21st century. This visualization shows the expected changes in temperature and precipitation we might see, compared to the average levels of the late 20th century. The largest temperature increases are seen in the Northern Hemisphere. Across North America, areas that typically have snow, such as the Rocky Mountains and northern Canada, will see the earliest and largest temperature rise. The warming temperatures will eliminate the reflective and cooling effect of the white snow cover. This reduction in albedo is the reason why the Arctic region shows such dramatic warming, as the polar sea ice melts and the darker ocean water absorbs energy from the sun. In turn, the warmer water accelerates the melting of the sea ice. All around the globe, the land areas show a greater increase in temperature than the surrounding ocean waters. Evaporation of the water helps to keep the ocean surface cool, and the deep depths of the ocean have a large capacity to absorb energy before heating up. Off the coast of South America stretches an unusually warm patch of the Pacific Ocean. A cyclical occurrence, known as El Niño, causes more precipitation in that area of the Pacific and affects the climate throughout the region. And we can see that happen in this visualization of changes in precipitation. Models project warmer waters and increased precipitation to stretch across the Pacific Ocean to Indonesia as the century progresses. The monsoons over the Indian subcontinent will bring increased precipitation over a wider area, and eastern Africa and the savannas of the Sahel could see precipitation increases up to 100%. At the same time, the Mediterranean will experience the opposite, a decrease over 40%. In general, the mid-latitude and subtropical dry regions are projected to see less precipitation, while the mid-latitude wet regions could see more precipitation. The poles and high latitudes are expected to also have increased precipitation. For North America, the models indicate more precipitation in the north and less in the south.
By combining data from various climate models used by the IPCC, this video shows the expected changes in temperature and precipitation for the 21st century. Projected change in ocean surface pH. Today, the average ocean surface pH is about 8.1. Projections suggest a further acidification of the oceans over this century due to increasing atmospheric carbon dioxide concentrations. Under a low emission scenario, RCP 2.6 on the left map, ocean acidification will be relatively limited. However, under scenario RCP 8.5, see the right map, a reduction in average global surface ocean pH of between 0.30 and 0.32 units is to be expected. This progressive acidification will harm marine creatures which form shells, for instance corals, and the species which depend upon them. Projected sea level rise. Global mean sea level will continue to rise during the 21st century. See the graph. The projected rise ranges between 0.26 meters to 0.98 meters, depending on the scenario. Under all RCP scenarios, the rate of sea level rise will exceed that observed during 1971 to 2010 due to increased ocean warming and increased loss of mass from glaciers and ice sheets. Projected Northern Hemisphere. September sea ice extent. During the 21st century, the Arctic sea ice cover will continue to shrink and thin as global mean surface temperature rises. Under scenario RCP 8.5, it is likely that the Arctic Ocean will be nearly ice-free in the month of September before mid-century. Projected impacts of climate change in Africa. Africa is one of the most vulnerable continents to climate change. Most of Africa will see less precipitation, with only the east central regions seeing an increase. By 2080, an increase of 5 to 8% of arid and semi-arid land is projected under a range of scenarios. Already by 2020, between 75 million and 250 million people will be exposed to increased water stress due to climate change. Agricultural production, including access to food, is projected to be severely compromised. In some countries, yields from rain-fed agriculture could be reduced by up to 50%. Sea level rise will affect major cities in low-lying coastal areas such as Alexandria, Cairo, Lomé, Cotonou, Lagos and Massawa. Projected impacts of climate change in Asia. This slide details some of the impacts of climate change projected for the Asian region. The light blue colour indicates permafrost regions that are at risk of thawing. Glacier melt will increase flooding and rock avalanches and affect water resources in Tibet, India and Bangladesh. This will then cause decreased river flows and fresh water availability as the glaciers recede. More than 1 billion people could have water shortages by the 2050s. Southeast Asia, especially the heavily populated mega delta regions, will be at risk from flooding. Around 30% of Asia's coral reefs are likely to be lost in the next 30 years due to multiple stresses and climate change. Changes in rainfall will increase diarrheal diseases, mainly associated with floods and droughts. The green colour indicates the possible increase in malaria distribution. Projected impacts of climate change in Latin America. This slide presents climate change impacts projected for the Latin American region. As a consequence of reduced precipitation and retreating glaciers, Latin America may have less water, affecting human consumption, agriculture, and energy generation. Yields of food crops may diminish, with adverse consequences for food security. Latin America also faces the risk of significant biodiversity loss through species extinction in many tropical areas. Decreases in soil water are projected to lead to gradual replacement of tropical forest by savanna in eastern Amazonia. Another ecosystem situated in the Caribbean at threat are coral reefs, home to many marine living resources. Sea level rise will increase the risk of flooding in low-lying areas, particularly the Caribbean. Projected impacts of climate change on small islands. Many small islands, for example in the Caribbean and the Pacific, will experience reduced water resources to the point where they become insufficient to meet demand during low rainfall periods. Sea level rise will lead to the infiltration of freshwater resources by saltwater, making it undrinkable. Sea level rise is also expected to exacerbate inundation, storm surge, erosion, and other coastal hazards, thus threatening vital infrastructure, settlements, and facilities that support the livelihood of island communities. The deterioration in coastal conditions and coral bleaching will reduce the value of these destinations for tourism. Carbon crossroads. This diagram depicts 4 potential climate futures, depending on what policies governments adopt to cut emissions. It is based on the 4 scenarios used in the 2013 IPCC report on the physical science basis of climate change. Global warming by 2100 and beyond, a function of cumulative CO2 emissions. The graph illustrates the linear relationship that exists between cumulative human-induced CO2 emissions on the horizontal axis and increases in global mean surface temperature on the vertical axis. In other words, more CO2 emissions lead to higher mean surface temperatures. Because we cannot tell exactly how much carbon dioxide we will emit in the future, different scenarios exist for what global temperatures will be at the end of the century. These scenarios range from 2 degrees centigrade, the blue line, RCP 2.6, to nearly 5 degrees centigrade, the red line, RCP 8.5. In order to have a greater than 2 in 3 chance of keeping global temperatures below 2 degrees centigrade, thereby avoiding dangerous climate change, cumulative emissions of CO2 must not exceed 1,000 gigatons of carbon, GTC. However, as of 2011, more than half this amount, over 500 GTC, has already been emitted on the black line. Further information. The horizontal axis on the bottom of the graph indicates cumulative emissions in gigatons of carbon, GTC, while the top axis indicates emission levels in gigatons of carbon dioxide, GTCO2. 1 GTC corresponds to 3.667 GTCO2. Section 5. Sources of scientific data. This section provides an overview of main sources of scientific climate information, relevant programs, and institutions. The Intergovernmental Panel on Climate Change, IPCC. The IPCC is the leading international body which synthesizes and assesses climate change knowledge. Established in 1988 by UNEP and the World Meteorological Organization, WMO, the IPCC assesses all peer-reviewed and published climate change information. Awarded with the Nobel Peace Prize in 2007, it calls on a network of climate scientists, biologists, economists, sociologists, etc. from every continent on Earth to produce reports on the state of knowledge of climate change science, analyze the social and economic impacts of climate change, and identify possible adaptation and mitigation options. Important reports published by the IPCC. The IPCC publishes various reports that are relative to the climate change regime. Widely cited, the comprehensive assessment reports review the latest science on climate change, its impacts, vulnerability and adaptation, as well as mitigation options. In addition to these reports, the IPCC also publishes special reports on selected topics, for example, renewable energy sources, extreme events and disasters, emission scenarios, etc. It also produces methodological guidance documents and technical papers. World Meteorological Organization, WMO, Global Climate Programs. The WMO runs a number of global climate programs that provide policymakers and technical staff with information necessary to successfully respond to climate change. The World Climate Programme, WCP, aims to produce skillful climate predictions and projections, develop operational structures to provide climate services, and to develop an essential global observing system to meet climate information needs. The WCP underpins the Global Framework for Climate Services, GFCS, which aims to incorporate science-based climate information into planning, policy, and practice on the global, regional, and national scales. Another major program is the Atmospheric Research and Environment Program, ARE, which coordinates and stimulates research on the composition of the atmosphere and weather forecasting, focusing on extreme weather events and socio-economic impacts. The Commission for Climatology, CCI, advises and guides the activities of the WCP while playing a key role in implementation of the GFCS. In focus, Global Framework for Climate Services, GFCS. The GFCS is a global partnership of governments and organizations that produce and use climate information and services. It seeks to enable researchers and the producers and users of information to join forces to improve the quality and quantity of climate services worldwide, particularly in developing countries. The presentation provides an introduction to the main elements of the GFCS. WMO Global Atmosphere Watch, measurement stations worldwide. The Global Atmosphere Watch, GAW program of WMO, provides reliable scientific data and information on the chemical composition of the atmosphere, its natural and anthropogenic change, and helps to improve the understanding of interactions between the atmosphere, the oceans, and the biosphere. The backbone of the GAW program is a global network of more than 80 measurement stations as seen on this map. WMO Regional Climate Centres and Outlook Forums. WMO Regional Climate Centres, RCCs, are centres of excellence that create regional products, including long-range forecasts that support regional and national climate activities. RCCs use data and products from global producing centres for long-range forecasts, GPCs, incorporating regional scale information. An additional main source of information for RCCs are data, products, know-how, and feedback they receive from National Meteorological and Hydrological Services, NMHSs. Regional Climate Outlook Forums, RCOFs, bring together national, regional, and international climate experts on an operational basis to produce regional climate outlooks based on input from national, regional, and global institutions. By bringing together countries having common climatological characteristics, the forums ensure consistency in the access to and interpretation of climate information. The information provided by RCOFs is being applied to reducing climate-related risks and supporting sustainable development. National climate data. National Meteorological and Hydrological Services, NMHSs, provide weather, climate and water information to emergency managers, national and local administrations, the public and critical economic sectors. The NMHSs make a significant contribution to safety, security, and economic well-being by observing, forecasting, and warning of pending weather, climate, and water threats. I do hope that you enjoyed this introduction to climate change science. We look forward to you engaging with all 4 of the other courses within our 5-module course. You are going to be the climate change leads, and you will make climate change interesting for all of your pupils so that we can share this valuable information to more pupils, more children, and we can get the entire world to understand how important climate change learning is for all our futures, our children's futures, their children's futures, and their children's futures. We can make a difference. Thank you.